Hello, AI enthusiasts. Welcome to a new deep dive. Building on our previous talk about feature importance, most videos on model selection treat it like a leaderboard race where the most complex algorithm always wins. In this video, we want to show something different, how the unique signature of your data dictates the tool you must pick, just like a master mechanic choosing between a wrench and a scalpel. By the end of this video, you will understand the physics behind choosing the right model family for any task. Think of a simple linear model as your screwdriver. You do not need a power drill for a tiny screw and a pair of glasses. When your dataset is small and the relationship between features is straightforward, linear models are the most efficient choice. They are fast to train and offer perfect transparency, allowing you to see exactly how each input influences the final prediction without any hidden complexity. Next, we have the pipe wrench, represented by tree-based models like random forests or gradient boosting. These are your heavy-duty tools for messy, tabular data. When your dataset has missing values, outliers, or nonlinear patterns, these models grip onto the underlying structure, where a simple screwdriver would slip. They are the workhorses of the data science world because they handle noise with incredible stability. For the most intricate tasks, we reach for the scalpel. Deep learning. Just as a surgeon needs a precise blade for delicate work, neural networks excel at finding patterns in high-dimensional data like images, audio, or natural language. However, a scalpel is overkill for fixing a leaky pipe. These models require massive amounts of data and computing power, making them a specialized choice rather than a default starting point. The volume of your data is the first major constraint. Imagine trying to build a skyscraper with only a handful of bricks. The most sophisticated architectural plan will fail. If you have fewer than a few thousand samples, stick to the screwdriver or the pipe wrench. Complex models like deep neural networks are data-hungry. Without millions of examples to learn from, they often perform worse than a simple regression. In the real world, speed is often as important as accuracy. Think of a high-speed delivery service. A bike is faster than a heavy truck for a single envelope in a crowded city. If your model needs to make millions of predictions per second, the computational cost of a deep network might be prohibitive. Sometimes, we deliberately choose a simpler tool to ensure the system remains responsive and cost-effective. In fields like medicine or finance, you often need to explain why a decision was made. This is the glassbox requirement. It is like a repair manual that explains every step of a fix. While a complex black box model might be slightly more accurate, a simple decision tree allows humans to audit the logic. If you cannot explain the model's output to a stakeholder, the most accurate tool in the world might be useless in practice. Choosing a model is a constant battle against noise. Think of it like a tailor. A suit that is fitted too perfectly to a person's temporary slouch will not fit when they stand up straight. If you choose a model that is too powerful for the amount of signal in your data, it will start memorizing the noise. By selecting a model with the right level of constraint, we ensure it learns the underlying patterns that will work on new data. It is tempting to use automated tools that try every model at once, but this is often a trap. It is like a robot trying to fix a car by throwing every tool in the shop at the engine. Without understanding the context of your problem, you might end up with a model that fails in the real world. A master mechanic knows why they are picking the wrench before they even touch the bolt. Model selection is not about finding the best algorithm because the best algorithm does not exist. It is about finding the right tool for your specific repair job. By looking at your data's size, noise, and speed requirements, you can move from guessing to making informed engineering choices. If you found this dive into the machine learning toolbox helpful, subscribe for more conceptual deep dives. Now, go out there and pick the right tool for your next project.